Good morning, students. In the last session, we discussed about one problem. So that by using different spectral information, we can determine the structure of an organic compound. In this video also, we discussed another problem based on molecular formula. Here, the molecular formula is C10H12O2. So first of all, we have discussed about double bond equivalence, the number of double bonds present in the organic molecule. The double bond equivalence is equal to Cn plus 1 minus Hx by 2. In the last session, we already clearly explained about double bond equivalence. So the double bond equivalence formula is completely depends on the elements present in the organic molecule. For example, if the molecule having only carbon and hydrogen, or if the carbon, hydrogen or oxygen, then the double bond equivalence formula is Cn plus 1 minus Hx by 2. If the molecular formula having carbon, hydrogen, oxygen and nitrogen, then we can add minus NX for nitrogen atoms. For example, if the molecular formula having halogens, then we can add halogen atom to the hydrogens. Then we can calculate double bond equivalence. So these are the these are the formulas for the determination of double bond equivalence. This is the double bond equivalence. This is not for double bonds. The double bond equivalence. That means here the cyclic system is also considered as a double bond equivalence. So that value is represents number of double bond equivalences, but not number of double bonds exactly. For example, if the molecule having the double bond equivalence having 4, this represents maybe one cyclic ring along with 3 double bonds. One cyclic ring along with 3 double bonds, or the molecule having 3 double bonds or 4 double bonds or 2 alkyl molecules, whatever it may be. But the double bond equivalence represents equivalence but not exact double bonds. So here the cyclic system is also considered as a double bond equivalence. Now we can calculate double bond equivalence by using the double bond equivalence formula. Now the molecular formula is C10H12O2. So here Cn plus 1 means number of carbons plus 1. Here in the molecular formula we have 10 carbons, so that Cn plus 1 means 11. And Hx by 2. In the molecular formula we have 12 hydrogen atoms, so 12 by 2. So 12 by 2 means 11. Sorry, 12 by 2 is 6. So 11 minus 6 is equal to 5. So 11 minus 6 is equal to 5. So this is the double bond equivalence. So this 5 represents maybe the molecule contains 5 double bonds. Maybe the molecule contains 5 double bonds or one aromatic ring along with another double bond. So here, for example, if the molecule having one aromatic ring, then the double bond equivalence for that aromatic ring is 4, because the well-known aromatic ring is benzene. So if the molecule having benzene, then the double bond equivalence for benzene ring is 4. Because the presence of 3 double bonds and 1 cyclic ring. So the double bond equivalence for benzene ring is 4. Here the calculated double bond equivalence is 5. Maybe in this 5, the double bond equivalence 4 for aromatic ring and the organic molecule contains another double bond. The organic molecule contains another double bond. Whether it may be carbon-carbon double bond or carbon-oxygen double bond. But along with one aromatic ring. So this 5 double bond equivalence 5 maybe indicates presence of one aromatic ring along with one additional double bond. That additional double bond may be carbon-carbon double bond or carbon-oxygen double bond. Now we can move into the ultraviolet visible spectroscopy. Already in the last session we discussed about what is the application of UV. So what is the application of UV? UV ultraviolet visible spectroscopy. So the application of ultraviolet visible spectroscopy is by using ultraviolet visible spectroscopy, that means lambda maximum values, we can determine the presence of chromophoric groups, whether the molecule contains chromophoric group or not. If the ultraviolet visible spectrum exhibits a lambda maximum value above 220 nanometers or 230 nanometers, definitely consists of at least one chromophoric group, whether it may be carbon-carbon double bond or carbon-carbon double bond or carbon-oxygen double bond or aromatic ring. Any other multiple bond system definitely contains in aromatic ring. So here the given value of UV is 245 nanometers. That means our organic molecule produces a peak at 245 nanometers. So 245 nanometers is above 220 nanometers. So definitely it represents the presence of one chromophoric group, whether it may be aromatic ring or carbon-carbon double bond or carbon-oxygen double bond. So definitely it represents one chromophoric group, whether it may be carbon-carbon double bond or carbon-oxygen double bond or aromatic ring. So that specific functional group, that means whether it is aromatic ring or carbon-carbon double bond or C double bond is confirmed on the basis of lambda max, epsilon maximalis. But here in our problem they didn't give the epsilon maximalis. If they are giving epsilon maximalis, then definitely we can confirm the presence of whether the 245 nanometers for benzene ring or carbon-carbon double bond or carbon-oxygen double bond. If for example the epsilon max value is very low, for example if they are given epsilon max value is 10, then definitely the 245 nanometers indicates the presence of carbonyl function group, because the epsilon max value is very low. That epsilon max value represents the transitions are forbidden transitions. For example, if the epsilon max value is about 10,000 or 20,000, definitely it represents the allowed transition. That means carbon-carbon double bond or benzene ring. So that 245 nanometers along with epsilon max value about 10,000 or 20,000, that represents that lambda max value is corresponds to aromatic benzene ring or carbon-carbon double bond, because in aromatic benzene ring and carbon-carbon double bond we have pi bonds. So then it is undergo pi to pi star transitions. So that is why. So that if they are giving the epsilon max value 245 nanometers along with epsilon max value, then you can definitely confirm that it is a aromatic ring or for carbon-carbon double bond. Now, so the conclusion for UV is here. The conclusion is, what is the conclusion? The 245 nanometers indicates definitely the organic molecule contains any chromophoric group, whether it may be aromatic benzene ring or carbon-carbon double bond or C double bond. That is the conclusion from these 245 nanometers. Now we can move into the IR. So what is the application of IR? Based on IR spectroscopy, we can determine the functional group present in the organic molecule. By using IR spectroscopy, we can determine the presence of functional group in the organic molecule. So here we have lots of values. One is 1730 centimeters. Already we are well known with IR values. So 1760 centimeters indicates, 1730 centimeters. 1730 centimeters indicates, 1730 centimeters indicates maybe the presence of C double bonded group in organic molecule. This 1730 centimeters indicates C double bonded switching frequency. So the C double bonded switching frequency indicates maybe the organic molecule contains one C double bonded group, whether it will be aldehyde or ketone or carboxylic acid. So that is further confirmed by NMR data or mass data. So but 1730 centimeters is definitely indicates the presence of C double bonded group. Maybe the C double bonded group is in aldehyde or ketone or carboxylic acid or in any other carbonyl containing functional groups. So that is not confirmed in the IR values, but it is confirmed in the later sessions by using NMR data or mass data. So now the second value is 1760 centimeters. So 1760 centimeters indicates C double bond C station frequency, indicates maybe C double bond C station frequency in aromatic rings or conjugated alkenes. 1600 centimeters indicates C double bond C station frequency in aromatic rings or aromatic skeletal vibrations or aromatic skeletal vibration. 2946 centimeters. So 2946 centimeters indicates CH station frequency in alkanes. CH station frequency in alkanes. That means whether it may be CH station frequency in CH2 or CH2 or CH3 or CH, whatever it may be, but that represents 2946 centimeters indicates maybe our organic molecule contains whether CH3 group or CH2 or CH2. And the 3030 centimeters. This 3030 centimeters, that means 3030 centimeters indicates double bond CH station frequency. Double bond CH station frequency in alkene molecule or aromatic ring. Double bond CH station frequency in aromatic ring or alkene molecule. Double bond CH station frequency alkene or aromatic ring. Now the values, the remaining two values, 700 centimeters and 780 centimeters. These are the two deformation values, because here the values are very low. So that is why these are the deformation values. These deformation values are corresponding to the CH deformations in aromatic systems. CH deformations in aromatic systems. So by observing all the IR data, like C double bond, C frequency, the carbon-carbon double bond, double bond CH, single bond CH and aromatic ring. By observing all the data, we concluded that based on IR data, what was the conclusion from IR? What is the conclusion? So by observing the IR data, definitely the organic molecule contains C double bonded group, and by observing the 1600 centimeter inverse, 3030 centimeter inverse and 770 centimeter inverse indicates the presence of aromatic ring. Definitely the organic compound contains one aromatic ring along with C double bonded O, and it contains any other functional groups, any other groups that is confirmed by using NMR data and mass data. So what is the conclusion from here? So the final conclusion is our compound contains one aromatic ring along with C double bonded O. So we are moving to the third spectral information. The third spectral information is NMR. So NMR is the very important spectroscopy technique to determine the organic molecule structure. So here we have 4 NMR sequences. That means here the molecular formula contains 12 hydrogens. So the 12 hydrogens are present in 4 different environments. One environment having 5 hydrogens, and the second environment having 2 hydrogens, and the third environment having 3 hydrogens, and the fourth environment having 2 hydrogens. So overall 12 hydrogens. So all these 12 hydrogens are split into present in our organic molecule as 4 different environments. Now let us see the NMR data. Here these are the chemical values and these are the number of protons in that particular environment, and this is the multiplicity. So here the chemical value is 7.3 delta, 5 hydrogens singlet. So already in the last session we have discussed about chemical values for aromatic benzene ring. So the chemical value for aromatic benzene ring is 6.5 delta to 8.0 delta. So if the molecule having aromatic benzene ring, the proton present in the benzene ring exhibits a chemical value at 6.5 delta to 8.0 delta or 8.5 delta. The chemical value is the chemical value of that benzene hydrogen is completely depends on the substitution which is present on benzene ring. That means if the benzene ring having electron releasing group, then the chemical value shifted towards lower chemical side. That means that it may be produces 6.5 delta, 6.7 delta, 6.9 delta. So because of the presence of electron releasing group, so it releases electrons, and the electron density on benzene ring will be increases. So it is shifted to shielding region. So the electron density around the benzene proton will be increases. So then it is exhibits a low chemical value. And if the benzene ring having high chemical values, if the benzene ring is substituted by the electron withdrawing group, then it is exhibits high chemical value, because the presence of electron withdrawing group withdraws electrons from benzene ring, and the hydrogen atoms on benzene ring gets electron deficiency. So that is why the hydrogen atom reside at high resonance frequency. So now the chemical value 7.3 definitely indicates benzene ring value. So this 7.3 delta indicates benzene ring value. So 5 hydrogens. So in the benzene ring we have 5 hydrogens. So that means our benzene ring having monosubstitution. So here the benzene ring is monosubstitution, because benzene ring having only 5 hydrogens and the remaining carbon is substituted by any other group. So what is the group? The group is determined by other spectral data. So this 7.3 delta 5 hydrogens singlet. This singlet represents multiplicity. So in some cases they are giving 7.3 delta 5 hydrogens multiplet, and in some cases it gives singlet. So whatever it may be, it represents benzene ring value, because sometimes all the sequences are overlap one by one, so that it is appears as a singlet. In sometimes it appears as a multiplet. Next, the NMR data is 2.9 delta 2 hydrogens triplet. So 2.9 delta 2 hydrogens triplet means 2 hydrogens. That means CH2 is adjacent to CH2. The triplet, the multiplicity is very important. The multiplicity indicates number of neighboring protons. Here, our environment having 2 hydrogens and it exhibits a triplet. So this represents the 2 hydrogens are adjacent to another CH2 group. So because of the presence of adjacent 2H2, 2 hydrogen atoms, these 2 hydrogens are split into a triplet. So this is the arrangement for 2 hydrogens triplet. And the third chemical value is 3 hydrogen singlet. So 3 hydrogen singlet means CH3. 3 hydrogens are in one environment, so that you can write CH3. So the multiplicity of this particular singlet is singlet. That means it is attached to one carbon and it does not have any number of hydrogen atoms, or maybe the CH3 group is attached to C double bonded O because this carbon does not have any hydrogen atoms, and maybe CH3 group is also attached to oxygen. What are it mean? CH3 is also attached to nitrogen. CH3 is also attached to sulfur. But I cannot write nitrogen and sulfur because in our molecular formula they didn't give the nitrogen and sulfur. So that is why I am not writing CH3 is attached to nitrogen. But in our molecular formula we have oxygen, so that why CH3 is attached to oxygen or CH3 is attached to C double bond. Because already we know that from higher data we have one C double bond group. So that is why here the CH3 group may be attached to C double bond group. So the next chemical value is 4.3 delta 2 hydrogen triplet. So already the second chemical value 2.9 delta 2 hydrogen triplet represents this CH2 group, and the fourth chemical value represents another CH2 group, because if this CH2 group is also HCl to another CH2 hydrogen atoms. So it is also as a one triplet. So for second chemical value and second NMR data and fourth NMR data, the common unit is CH2 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 CH2. So from all the discussion from NMR we have one monosubstrate benzene ring and one CH2 CH2 and one CH3. It may be attached to C double bond or CH3 oxygen. So let us confirm that whether it is attached to C double bond or oxygen. Now let us see the molecular formula. The molecular formula is C10. That means the organic compound having 10 carbon atoms. Here we have 6 carbon atoms and we have 2 carbon atoms. So total 8 carbon atoms and CH3 9 carbon atoms. If the CH3 is attached to C double bond, then the number of carbons is 10. So that CH3 is attached to C double bond. Why the CH3 is attached to C double bond? Why we can confirm that the CH3 is attached to C double bond but not oxygen? If the CH3 is attached to oxygen, then the chemical shift value is APS at nearly 3.5 delta to 4.0 delta, but the given chemical shift value is 2.08 delta. So that is why definitely CH3 is attached to C double bond. But here, if the CH3 group is attached to another carbon atom and it does not have any alternative triangle or any hydrogen atom, then the CH3 group appears at a triplet at 0.9 delta to 1.0 delta. So that is why we can exclude this CH3 and C. And CH3 does not attach to oxygen atom. So based on this explanation, we can confirm that the definitely CH3 is attached to C double bond. So by observing or by the all about discussion, we have 3 points. What are they? One benzene ring and CH2 CH2 and CH3 C double bond. What are they? One benzene ring, CH2 CH2 and CH3 C double bond. Now the molecular formula is C10. So that the total 10 carbons and the number of hydrogens is 12. So 5, 4. 5 plus 4, 9, 9 plus 3, 12. And the number of hydrogens present in the molecule is 2 oxygen atoms. But here we have only C double bond O, only 1 oxygen atom. That means the organic molecule having another oxygen atom. So that finally you can write the moieties present in the organic molecule is 1 benzene ring and CH2 and C double bond O CH3 and 1 oxygen atom. So these are the units. So now we just connect one unit to another unit without disturbing the multiplicity. Just we connect one unit to another unit. So here just see the last NMR data 4.3 delta 2 hydrogens triplet. So already I said that if the carbon atom having hydrogens, it is attached to oxygen, then it exhibits a chemical shift value at 3.5 delta to 4.5 delta. So here the chemical shift value is 4.3 delta. That means these 2 hydrogens are definitely attached to 1 oxygen atom. So here we have 1 oxygen atom. So here we have CH2 unit. In this one CH2 is attached to definitely oxygen atom, but other CH2 is attached to any other group, because if this CH2 group is also attached to oxygen, then definitely these two are in same environment, but they are due to different environments. So that is why this CH2 is definitely attached to different environment, because the chemical value of this 2 hydrogen triplet is different from this 2 hydrogen triplet. So here this 2 hydrogen triplet appears triplet at 4.3 delta, and this 2 hydrogen triplet appears at 2.9 delta. So these hydrogens appears triplet at 2.9 delta, and these hydrogens appears at 4.3 delta as a triplet. So these are the 3 units: one monosubstrate benzene ring, CH2, CH2O, and C double bond O, CH3. So these are the 3 units. Now let us connect one unit with another unit without disturbing the multiplicity. So now write the monosubstrate benzene ring. If I connect this C double bond O, CH3 to this C double bond monosubstrate benzene ring, then the structure is concluded. We have remains with the CH2, CH2O, because if it is attached to C double bond CH3, then there is no position to attach CH2, CH2O. So definitely we cannot attach the C double bond CH3 to monosubstrate benzene ring. So then we can attach CH2, CH2O. So this is one unit, and we have remaining one unit, C double bond O, CH3. So we have one valence. So now I can attach C double bond O, CH. So this is the connectivity of the following moieties. So we can also write another structure based on these moieties. For example, if the oxygen is attached to benzene ring and CH2, C double bond O, CH3. Maybe this is also a structure, but by observing the chemical shift values. The chemical shift values of benzene ring. Here, the chemical shift value of benzene ring is 7.3 delta. For example, if the benzene ring is attached to electron releasing group, that means here the benzene ring is attached to oxygen. So oxygen having lone pair of electrons. So then it is undergo conjugation. So it produces a negative charge on aromatic system. That means it implements electron density on aromatic benzene ring. So then the hydrogens present on benzene ring appears a singlet or multiplet at low chemical shift values. That means at 6.8 delta or 6.7 delta. But the given chemical shift value for benzene ring is 7.3 delta. So the basic value for aromatic benzene ring is 7.25 delta. So here the CH2, it is not strong electron releasing group, not a strong electron ring. It is a moderate electron releasing group. It releases electrons to electron. So that the electron density on the benzene ring is much not different when compared to normal benzene ring. So that is why it appears at chemical shift value at 7.3 delta. So based on the chemical shift value of aromatic benzene ring, actually we get two structures based on these two units. But actually the chemical shift value of benzene ring we can conclude at first structure. That means benzene ring is fused with CH2, CH2O, C double bond O, CH3 is the correct structure for the organic molecule. Let us see the mass fragmentation of this molecule. Let us see the mass fragmentation of this molecule. So already in the last problem we discussed about mass fragmentation and importance of mass fragmentation. Here the structure is CH2, CH2O, C double bond O, CH3. What is the principle involved in mass spectrometry? You just bombard with the molecule with 70 electron volts of energy. So then it produces a molecular ion. So the molecular ion is exhibits a molecularity M plus radical. So it is 77 plus 14 plus 14, 28. C double bond CH3 is 43 and oxygen is 16. So total is 9 plus 8. 17 plus 7, 24, so 4, 2, 9, 11, 12, 12 plus 4, 16, that means 164. So the compound exhibits a molecularity at 164. The molecular weight of this organic molecule is 164. Now it is undergo further fragmentation. Now it is undergo further fragmentation. Maybe it loses one radical as CH3CW1 radical, and it appears as a positive charge. That means CH2O positive, but it is exhibits a very low intensity signal because the formed alkoxide ion is very less stable. So that is why this fragmentation is very rare. And then it is undergo fragmentation, like it loses this alkoxide radical, and it is appears as a CH3C2 bond plus, because here the molecular, now we can represent the molecular oxygen atom. It is undergo homolytic cleavage. If we have done homolytic cleavage at this carbon atom, then this carbon gets one radical, oxygen already carries one radical. This radical combines produces one triple bond, and it is already having one positive charge. So the positive charges species are recorded in the mass fragmentation. So that it exhibits a peak at temperature is equal to 40. So like this. So you can also done fragmentation of this carbon atom. So if it is loses one radical, then it is counted to be a benzyl carbon. So CH2 plus, and it is undergo scrambling, and it exhibits a, and it is counted to be a nuclear cation, and exhibits a peak at temperature is equal to 91. So this is the fragmentation process for this organic molecule. So we have different modes of fragmentations. So we have to apply all the fragmentations and can get different fragment ions at different temperature values. So finally, by observing the UV data, so what is the conclusion of UV? The UV lambda max value is 245 nanometers. What I was said that the 245 nanometers indicates the presence of chromophoric group. Here, observing the molecule, we have one chromophoric group, that is CW bond or benzene group. So usually the 245 nanometers indicates the presence of lambda max value for benzene group. Usually that 245 nanometers value is for benzene chromophoric group, but not carbon chromophoric group. Okay. And the IR data represents 1730 cm, 1600 and 3030 centimeters. All these things are already discussed in IR, and all the data was satisfied by the structure and confirmed by the mass spectral fragmentation. So finally, the structure of an organic compound is like this. Thank you, friends. Thank you.